need like a break or anything, right? Okay. Just take a big deep breath, because we're going to go really technical, and I'm not talking about business at all. Okay? How many people are software developers here? How many people write Python? How many people write Rust?
I did the advent of code.
That's right. What about web devs? You know, TypeScript. Okay. So I'm going to be strictly talking a lot of big data engineering technologies. I'm going to run through a bunch of resources here as if, you know, I'm prompting ChatGPT just to tell you like what are my like canonical references for building this project. And that's going to just kind of lead me into what it is and go from there. A lot of you guys know what Pydantic is. It's awesome. Helps you write schemas, essentially, that you can then validate. And a lot of people use that for websites and stuff, but you know, you're pretty much staying in the Python domain the entire time, and Python isn't necessarily important or performant, and so that's why you use like libraries that do more performant things, and that's what I do for this project. Another fantastic couple of resources for people who are vibe coding with Python that I think is really important to know about are design patterns in Python, and these are, you know, after however many months that I was, you know, vibe coding over the last 2 years, I found these, and they're like, you know, the canonical references that I would consider. So take a look at them. Esper is the ECS component engine that I initially referenced to build what you guys are eventually going to see. Just to get the project out of the way, I've built Archetype, which is an entity component system that uses lazily evaluated data frames. That uses a Rust backend on big table formats that to essentially scale large simulations, and then to also scale on Ray. So I don't know if you guys, how many people know what Ray is, the workload orchestration? Okay. So ECS is a really convenient way of writing simulations. It's a design pattern in software, and you can write it in, and this has been done, you know, Unity has done this, there's a lot of different gaming engines. Essentially, your components, if you think about your components as Pydantic models, they're your schemas, they're your state, and you put them into these, you know, blocks, and you can combine them, and it's fun to do that. And then your entities are these strictly just integers that are kind of mapped with your component, your schema. And then when your simulation runs, that entity ID is like actually populates that state against that schema, and then you have like an entity with that state. The system part of an entity component system is the actual decoupled processor that's updating that state every step. Okay, so a simulation engine is basically, you got the state at step n-1, and then at step n, you're looking at step n-1, and you're performing some transformation over it. Okay, and that's, I'm going to be showing you a very small toy example, because up until about 2 weeks ago, none of this was working. And thank God, Cloud 4 came out.
Yes.
Okay, and I got the synchronous example working, which means I've got essentially 2 for loops. I've got all of my tables for my archetypes. So the next thing I have to describe is, so you have entity component system, and that decouples, you know, your processors from your state, so you can define them, you know, declaratively. The archetype system is takes the exact combinations that you're populating your simulation with, and that exact combination essentially defines the archetype, and you just save that as a table, so then you have like atomic querying and reading from the same table. So what that looks like if you have like a simulation that's updating your position based on a velocity, is you would have an archetype that's like position velocity. Or if you have an archetype that's just position, and you'd have a different table for just position. Anyway, we're going to get into some code here soon, I swear. I found all of these resources just browsing online, asking ChatGPT, and doing deep research. If you don't know what Apache Arrow is, it's a columnar format that's highly performant, specifically for data engineering, and it enables zero-copy reads and writes. What that means is any transformation that when you read from storage, you do something with it, you're pulling that data into memory, and then any small iterative transformations that you're adding on top of it are essentially appended. It doesn't actually have to copy all of the data in order to do it, because that would be cost prohibitive for enterprises that are running large workloads at scale. My background is in big data engineering. I worked at Lucid Motors. We were running large-scale Spark pipelines, and managing Spark clusters is a pain in the ass. So that's why I really like Daft, which is a distributed query engine that has the Rust backend, and it has similar semantics to pandas, right? A lot of people know pandas, but it doesn't. But it works locally as well as on Ray. So you can actually do work without having to run a cluster in Spark. Then all of these technologies, Ray, Apache Arrow, and we'll say Apache Iceberg if you're really deep on the data engineering. I'm not going to get into that. Power projects like Delta Cat, where the AWS Glue team essentially collaborates with Daft and the Ray team to create this exabyte scale. Let me just say that again. Exabyte scale data catalog to enable ACID transactions on tables. Okay. So these are the technologies that I chose to use, because what I'm betting on is that I can't work faster than a whole team of engineers, but if I have the right opinionated tool set, then I might be able to eke out some crazy performance and leverage these awesome open source projects. Okay? So definitely go check out Daft. The other technology I'm using is LanceDB, which is also a table format, but it's also a vector database. So instead of holding all of your vectors in memory in a running process, it's a table format, and you're only ever having to work with the data that you need, because big table formats decouple processing and compute. All right, my project is Archetype, and literally I started this project in January when I finally realized that this is what I wanted to do. And the whole purpose of Archetype is to power multi-agent simulations at scale. Now when I say agent, I do mean your LLM-based agents. Although more formally, I'm talking about agents in the general sense, the academic sense, where you have different cognitive architectures and things all the way down to just small rule sets like Conway's Game of Life, right? So Archetype leverages these technologies, and we're just going to jump right into my synchronous and asynchronous simulation examples. Okay? So I probably spend too much time on code aesthetics and getting design patterns right, and going through all of that and going through the process of just being comfortable with debugging was super worth it, because I feel very fulfilled having gotten to this point. As of maybe 3 hours ago, the asynchronous demo was not working, and was still debugging, and then on my way here, Claude 4 debugged it for me, and then got my asynchronous simulation working. So we're going to get to go and see that. Okay, so fundamentally, in every simulation, you've got a couple components that you need to describe, which are your schema for the state that you're wanting to hold for your simulation. Right? And then you'll have some processor, any component system that's a system.
Can we zoom in so we can see?
Oh, yeah. right, so that looks familiar, right? That's essentially pydantic. That's because my components are essentially just Lance models. Oops, Lance models are pydantic models that convert their schema to a pi-arrow schema automatically for me. And it also works natively with LanceDB, since LanceDB uses pydantic not only for structure generation with their large language models and for embeddings, but also just to define schemas for their tables. So the declarative fun syntax that pydantic has, you can now describe in your components, and it'll convert to an Apache arrow schema, which actually looks a lot more like this. I think we would all much rather write the former. And the symbol simulation, we have a movement processor where we are simply updating the position each step based on the delta t that we pass in. And this syntax here is essentially applying an expression on top of the input data frame that does not materialize until it's written to the archetype table that it belongs to. So you don't need to know which archetype you're trying to process. You don't need to know what table. You don't need to know any of that. And so what you're trying to do is separate and decouple all of your concerns. When you set up the simulation, because all we've done is defined two components in a processor, we need to create a simple world, okay? A simple world we'll get to. We need to add the processor to the world, and then we're going to spawn some entities into the world. Now, the entities, we're passing in these pydantic model instances, which is nice, as opposed to having to pass in pi-arrow instances or something like that. And then in a for loop, we'll just run world.step with a particular DT. You can put any args or words in here, and we'll just run this. So the first thing that I'm going to move into, it's a rogue breakpoint, is what's that one? Let the demo gods be kind to me. Okay, so a world, what is a world? Especially in most game engines, it's just a facade for all of the craziness and complexity that's underneath. Except for one thing, that it needs to step and orchestrate the querying of the data from the table. It needs to process the processors in their priority order, and then it needs to go right back to the table. But it's delegating all of that to separate classes in order to separate concerns. So we've got all of that kind of written in there, and we have a bunch of facade methods where we've taken, with dependency injection, right, these other classes that I'm going to show you in a sec, and we use those with just essentially these wrapper functions to make it clear. Okay? Now, the store is the farthest thing from the world, but it's where all the complexity is. This is where all of the big data technologies and things have to get integrated, and it has all of these different helper functions to make us convert between components and archetypes. Now, all of that's cool, but at the end of the day, what we really care about is the system that's running our processors. Okay? A system is going to hold processors that you add to it, and it's delegated through the world, and then you need to execute those processors. So effectively, you get we have some archetype signature